Welcome to Usability in Human Factors Information Visualization. This is Lecture A. By the end of this unit, learners will be able to 1. Define what information visualization is and what it is not. 2. Understand different ways to present different types of information, from simple to complex sets with multiple variables. 3. Discuss how to visualize information that is inherently hierarchical. 4. Understand ways to design not only static visualizations that don't change over time and dynamic visualizations that also allow users to interact with them. 5. Understand dimensions of visualizing medical data. The amount of information people consume in their daily lives is increasing every year. Scientists estimate that currently it averages quintillion bytes, or discrete pieces of data per year. That translates into 250 megabytes for every man, woman, and child, or every age, education, and economic status. Printed documents constitute only a very small portion of that data, leaving the majority of it to the digital realm that does not have direct physical manifestation. This is particularly the case for a person whose job it is to process and create knowledge. They have to rely on information coming from multiple sources. The ability to process it and make correct decisions or select appropriate action is essential to their performance. Not surprisingly, clinicians are increasingly included in that category. Nowadays, they rely not only on directly collected information from their patients, but also on large volumes of aggregated patient-related data. Multitudes of clinical journals discuss the advances in medical sciences, new monitoring devices that are capable of collecting more information about each patient, and integration of electronic health records make available patient data over the course of their lives. And clinicians are expected to be able to access it, analyze it, and select appropriate action. The good news is that human beings developed very complex perceptual systems to deal with the complex physical environment around them. Human vision is incredibly fast. It is highly parallel. We can perceive many things at once. We have a great ability to recognize patterns. Oftentimes, we notice things without consciously looking at them, which is called pre-attentive perception. It far extends our memory and cognitive capacity. And there is a growing body of evidence that people think visually. All these properties make vision a great resource to use in the design of computing applications. Let's look at this example. This is a very common way of presenting data in a table. This table contains census data, specifically average education level and income in different states. Can you tell me which state has the highest income? Is there any relationship between income and education? Let's try this again, now looking at a relatively simple visualization of the same data. Now its salient properties become more apparent. We no longer need to rely on serial search, scanning the table one item after another. We can quickly grasp the relationship in the data just by looking at the graph. Given that example, we can say that information visualization is really a way to support human cognition. It requires understanding of decision-making practices in a particular domain. Understanding helps designers to develop tools that present data in a way that improves understanding and insight, and helps to convert data to information and then to knowledge. Now, a few words about what it is not. Information visualization is different from visual design in that it really primarily focuses on supporting cognitive processes. It is different from user interface design or information architecture. Not all interfaces involve information visualization, although many do. Finally, it is different from scientific visualization, which is primarily concerned with physical representation of physical objects, for example, medical imaging. In contrast, information visualization is concerned with information, which does not have physical properties. Visualizing information includes two main components. First, it involves taking items with no direct physical correspondence and mapping them to 1, 2, or 3-dimensional physical space. Second, it involves giving information a visual representation that is useful for analysis and decision support. Since visualizations are meant to support different cognitive tasks, it is important to understand the nature of these tasks. Researchers in information visualization identify a large number of these basic tasks that include, for example, identifying objects, distinguishing between different objects, and more. It also includes mapping them to functions of visualization displays, such as overview, zoom, etc. We will talk about these functions in greater detail in the lecture. Here are two examples of information visualization that became popular. One is Smart Money, which visualizes complex data on performance of financial markets. The other one is An Architectural History of Manhattan. Both of these visualizations are interactive, and you can find them online. At the heart of information visualization is data. The most popular way to present data is on a table. Tables are great for databases where you can write automated scripts to query them. However, they provide minimal decision support for people. There are several types of data, and it is important to distinguish between them when thinking about visualization. There are many ways to think about data types. We will talk about one of the simplest taxonomies, which is nominal data. Nominal data is any qualitative data that simply includes categories, for example, names of states or people. Ordinal data presupposes some order to it, for example, age categories, 18 to 20, 21 to 35, etc. Numeric data is any data that has a numeric value, for example, age of individuals. Finally, metadata is data about data, for example, its type. Once we have a set of data, one of the most critical characteristics of this set that will suggest particular approaches to visualization is how many variables it includes. We will differentiate between univariate sets that include only one variable, bivariate, trivariate, and multivariate sets. The reason we don't really distinguish beyond 3 is that by then we have utilized all the dimensions of our 3-dimensional space for developing visualizations, so anything beyond that requires creative thinking. As you can probably guess, the majority of data sets you might encounter in the real world are multivariate, and they present a set of challenges. The ways to represent them usually include graphs, charts, in which structure and relationship between entities are important, maps that favor spatial organization, diagrams, which feature schematic properties of objects or entities, and glyphs, or visual metaphors, that allow us to map variables to particular visual properties. Univariate sets are the simplest sets you will encounter. Many of the everyday visualizations you see, for example, line or bar graphs, deal with univariate data. Bivariate sets are more complex. They include 2 variables that often have some dependency. The purpose of the visualization is to make that dependency apparent to the naked eye. For example, if there is any dependency between price of car and its mileage, a scatterplot would make it possible to see it. As you add more dimensions, simple visualizations quickly become messier. For example, here we add another dimension to include another component, horsepower, to our scatter plot. However, three-dimensional plots usually are relatively difficult to interpret due to such issues as occlusion, when some elements of visualization block others. An alternative to increasing a number of dimensions is to manipulate other visual properties. For example, here we use spatial orientation for price and mileages, and size of a visual element for the third dimension, such as horsepower. As we discussed earlier, most of the real-world datasets include multiple variables. Visualizing these datasets is non-trivial and often requires creative thinking. Most importantly, the visualization should be designed to support the tasks and activities of users. The easiest way to represent multiple variables is to give each a separate display and combine these displays on the same screen. For example, stacked timelines are a common way to represent several types of time series data together. Here's one example of different variables displayed in different scatterplots. While quite complex for a novice, this rich visualization could allow an expert to distinguish important properties of data. Star plot is another way of visualizing sets with many variables. In this visualization, each variable receives its own coordinate axis, all coming from one central point. The small charts on the right show how star plots can be used to help monitor changes in many variables over time simultaneously. Parallel coordinates is another visually compelling way to represent hypervariate data. Similarly to star plots, here each variable receives its own axis as well. However, instead of radiating from a central point, they are shown as parallel lines. Here are some examples of parallel coordinates. Another way to represent multiple properties of data in the same visualization is to use metaphors. Here is an example of planned attendance meetings represented by schematic tables with coffee cups. Each table represents a meeting. Full cups represent how many individuals of those invited accepted the invitation. Empty cups show individuals who rejected meetings, and upside-down cups show individuals who have not responded. This visualization has been shown as promising for individuals of older age and lower education. This concludes Lecture A of Usability and Human Factors Information Visualization. In this section, we reviewed the history of information visualization, and then we examined two examples of data sets, multivariate data sets and hypervariate data sets. Our next unit, we will discuss scaling and time scaling.